Well, good day, ladies and gentlemen. This is the second part of the series of lectures on measuring the difference in mean scores, the case of the analysis of variance. The objectives for today are to continue on with the discussion about the F distribution and then to begin a discussion about the degrees of freedom, to show you how to read an F distribution, how to calculate the grand mean, sums of squares, mean ratios, and F ratio of an analysis of variance. These are the most important components of the analysis of variance, and they're all included on a source table, which you will also have to learn how to read. We'll spend quite a bit of time on doing planned and post hoc comparisons because the fact is that an analysis of variance is an omnibus type of an analysis and you really don't know where the differences are, so you have to do it by using these planned and post hoc comparisons. Then we'll move forward into a two-way analysis of variance, and for the first time we'll look at two variables and how it predicts our outcome, our numeric variable. And then finally we'll talk about the different components of an analysis of variance test. We went through about 5 of the 7 on the first time through, but we'll review them in the context of a two-way analysis of variance. So let's move on to the F distribution. Well, you might say, well, how am I supposed to remember all these numbers? Well, there's a bit of a trick in a mathematical coincidence, and it's really not even a coincidence. It's something that mathematically is something that you can prove using advanced algebra and calculus, but since I didn't make it through much further than high school algebra, I'm not about to do that, and since I'm not going to do it, I'm not going to require you to do it. So here's the unique fact that you could use to remember what the critical values of the F distribution are. And that is, if you think about the T distribution and the Z distribution, the critical value for a 5% error rate is 1.96. If you take the square of the T value, or the T distribution, you come up with 3.84. And it is a mathematical truth that the square of the T distribution is equal to the F distribution. And the T and the F are both related in the sense that they work around variability and comparing the mean scores using variability. So it's not a surprise that the F distribution and the T distribution are similar. So just as with the T distribution, if the obtained value is less than the critical value, in the F distribution, if the obtained value is less than 3.84, that means that the alpha error is greater than 5%. On the other hand, if the calculated or the obtained F value is greater than 3.84, then the probability is less than 5%, or P is less than 0.05. And so in most instances, if you set your a priori error rate at 5%, then you would say that your statistical test is statistically significantly different, and that the mean scores, the omnibus test, says that one of the comparisons is different from the other with regard to the mean score. So the other thing that I wanted to show you is that the F distribution, just like the T distribution, varies depending upon the degrees of freedom. And so it varies in the height, and it also varies with the distance that the F 5% or the critical value is away from 0. So if you look at the F value of 10 degrees in the numerator and 1 in the denominator, and we'll talk about these more in depth in just a second and what those mean. You see that the critical value is out here past 3.8. Okay, folks, now let's take a look at what this all means with regard to the different types of distributions within the F test. The first thing that I'd like you to do is to turn to your textbook on page 367, and you'll see table A4. Now, what I want you to do is to take a look at these different F distribution graphs. And you'll notice up here what they have is F10-1, F10-3, 10-10, and 10-100. And it's associated with a different color on each of these particular distribution in the graphs. Now, the first thing that I'd have you remember is that these distributions are really a function of sample size in the F distribution, just as it is in the T distribution. So if you recall on the t-test, if you had a small number of persons in the study, therefore a small number of degrees of freedom, the t critical value at the level of alpha error of 0.05 was larger, and as the number of people in the study increased, or the number of degrees of freedom increased or got larger, then the critical value actually got lower, to the point where in the tables it showed that with an infinite number of persons enrolled in the study, and see, if you think about it, that's what we're talking about with an infinite number of random samples from the sampling distribution, then the t value was the same as the z value, which was 1.96. Now, if you look at page 367 and you look under the table and you look across near the top in the center of the page, you'll see something that says degrees of freedom numerator. And that's what you have with the 10 on the right hand side. And then if you look where it's after it says comma, and then you look at the number 1, well, that's the degrees of freedom in the numerator. So if you go across where it says the area is 0.05 in the row which says a denominator of 1, and in the column of 10, you'll see where it says 241.9. Now what that means is that the critical value, in order to be statistically significant, the obtained value has to exceed 241.9 in order for your test to be statistically significantly different. And so you can see from this value here that this red line is greatly extended compared to, for example, the green line, which is closer to the 0 point on the left hand side, and the green line with an F of 10 and a denominator of 100, so we don't have 100 here, so let's look at 120, which is right above the infinity sign on page 367 in the far left hand column of the text. And you'll see at 10 versus 120, you'll see that the 5% confidence or alpha error critical value is 1.91. And so what you'll see then is that the 3 and the 10 and all of those are in between then that 241. So the 10 comma 3, the critical value is 8.79, and in the 10 comma 10 distribution, then the critical value is 2.98. So as you can see, the F distribution, again, just like in the T distribution, varies depending upon 1, in this case, the number of groups, and 2, the number of people in the group, or in this case, the denominator degrees of freedom. And we'll talk a lot more, as I said just a second ago, about the degrees of freedom in the F distribution when we actually get to the actual calculations of the F ratio. So the thing to remember with an F distribution, much the same as you would have with the T distribution, is that they both differ depending upon the degrees of freedom, and the critical value you'll find is smaller or larger depending upon the degrees of freedom. Okay, let's pick up where we left off. This table is similar to the one that you have on page 367 of the textbook, but there's a couple of things that I'd like to point out. It's sometimes easier for people to look at the numbers and make sense of it than it would be for the folks to look at a graph or that type of a figure. So let's go ahead and look at the F distribution table here, and let's see how it compares to the F distribution. Now, what I want you to do is, as in the page table A4, you look across the top here, you have the numerator and the degrees of freedom. And on the far left-hand side here, we have the denominator in the degrees of freedom. And across here, we have 1 through, in this case, instance 9, whereas in the book we had 10. This is 1 minus the number of groups. So in our example in the textbook, we're really looking at 2. Now down here what we have is the A stands for basically the area under the curve. And this one, the 0.5, means that there is no difference whatsoever, that the probability is 50-50. Here it's the probability of a alpha error is 1 minus 0.90 or 10%. Here it's 1 minus 0.95, which is a 5% error rate for the alpha error. And down here, what we're looking at, again, this is the number of degrees of freedom. And down here, just as we had with a t-test, with a nearly infinite number of patients in a study, or a large number of patients. So what I've done is I've taken the two extremes, only 1 in the denominator and infinity in the denominator, so that you can begin to compare the numbers in these two sets of distributions. So first, again, look at the numerator. Again, the numerator is the number of groups minus 1. The denominator then is actually 1. Well, we'll get to it in a couple of minutes, but it's actually the number of people minus 1 minus the number of group. Now let's go ahead and look at the 95% figure, which is the 5% error. There's a couple of things we'd have you notice. First of all, and this is a little bit different, it's that we have with one group and 1 degree of freedom in the denominator, the critical value that you would need in order to declare your statistical test to be statistically significantly different. So the F ratio critical value here would be 161. With 2 groups, it would be 200. 3 groups, it would be 216. And as you can see, that as you move to the right with a larger number of groups, that the F value that you would need to obtain increases. Now let's look to see what it is like with an infinite number of persons, or again something which is a large sample size with a 5% error rate. With 1 degree of freedom, you have an F ratio of 3.84. So again, think about what I showed you with regard to squaring of the t-test, 1.96 squared, the infinite number on the t-test or the z distribution. The 1.96 squared is 3.84. But isn't it interesting that as you move to the right now, as the number of groups increases, the F critical value that you need to attain in order to declare your test statistically significantly different with your a priori error rate of 5%, that the critical value actually goes downward in this F distribution table. And if you go back to 367, what you'll see is, in this 1.95 with 1 degree of freedom, it's 161. With 2 degrees of freedom, it's 18.51. With 3 degrees of freedom, it's 10.13. So as you can tell, then the critical value goes down as the number of people in the study increase, again, similar to what you would find in the t-distribution. All right, the next step is do the calculation. Now, I'm going to go through this one example, but in most cases, what you will do is use the computer. The calculations for the analysis of variance are very complex. You can do them by hand, but we're not going to do that in the class. So we'll do it real quickly here in this one example, but you will not have to do it for examinations. Steps in the calculation of the analysis of variance is first you calculate the grand mean. Then you calculate the sums of squares, and the sums of squares, remember, is what we did early on when we learned how to calculate the standard deviation and the variance. It's the sums of the squares, and then we talked about the different types of error, the among groups error and the within groups error. Now in the F ratio, then what you do is you calculate the mean squares from the sums of squares. then you calculate the F ratio, and then the degrees of freedom, and then based upon the degrees of freedom and your F ratio, you compare that to the critical value to decide whether you have statistical significance or not. So let's start off then with the calculation of the grand mean. First, again, look at figure 7.2 on page 166, and this has the information that we will be using in the table, in table 7.2, to work through this problem. One way of calculating the grand mean, as you know, is to take every individual score. So in this instance, there were 73 individuals. Divide it by the number of individuals, and you come up with 14.78. In this instance, in the textbook, they had already calculated the mean score, the mean score for each group. So then another way of calculating a grand mean is to take a weighted group mean. So in this instance, in group A, they had 20 individuals. The weighted group mean was 13.5. In group B, they had 18 individuals, and group's B mean was 14. In group C, they had 35 individuals, and the group C mean was 15.89, divided by the number of persons in each group. So you can see that this is the 73. So you come up with an overall mean of 14.78. So the next step then is to calculate the sums of squares. First of all, you calculate the sums of squares among the groups. So in this instance, the sums of squares among the groups, so that's the A, divided by the number of groups minus 1. So in this instance, what we have is 20 people in the group A, just as we did before. Then we take the group mean, which was 13.55, subtract it from the grand mean, which is 14.78, and you square that, and that gives you part of the sums of squares among the groups. You do the same thing for group 2, so it's 14 minus 14.78, and then you do the same thing for group 3, so it's 35 times the square of 15.89 minus 14.78. Since there are 3 groups, then in this instance it's 3 minus 1. So the mean squares among the groups is 84.33 divided by 2 is 42.17. So the next thing that we do is we calculate the sums of squares within the group. So if you think about this in that graphic depiction earlier on, we take the difference then between each individual score and times the standard deviation. So in this case, the short form for this is you have n minus 1 person, so there was 20 people in group 1, so it's 20 minus 1 is 19, times the square of the standard deviation, plus 17 times the square of the standard deviation of group 2, and then 34 times the square of the standard deviation in group 3, divided by the total n of each group minus 1. So it's 19 plus 17 plus 34, so you see it's the same here. So that gives you a score of 246.99 divided by then the 70, which gives you a mean squares of error is 3.53. So the key here is that this standard deviation is what you get by subtracting the difference between an individual score and the mean score within each group and squaring that times the number of people. So this is how you get the mean squares within each then of the 3 groups. In order to get the F ratio then, you take the mean squares among the groups that we calculated in the first step, divided by the mean square error. So this is the 42.17 divided by the 3.53 gives you the F ratio of 11.95. So is it statistically significant? How can you tell? Well, okay. Well, then let's take a look at another lecture objective. And that objective is to be able to complete an ANOVA source table by calculating and providing values that are missing. Now, I'm not going to ask you to calculate all of these figures from scratch, just as I did a couple of minutes ago. But there is a convention for the table that does make some sense, and that you would be able to calculate values that should go into this table according to that convention. Also, if the analysis of variance statistics are reported correctly, you will see this convention in the article. And unfortunately, I'm going to show you some examples later on where the complete information is not provided in this format, and then I'll show you some other situations where it is provided correctly so that you can see the difference. So let's take a quick peek at it here using the same numbers that we've been using all along. So this is the convention for the analysis of variance table, and I've put into it then the numbers from our example in the textbook. This is what you're most likely to see in an article if the article prints the analysis of variance table. So if we think about what we had before, we have the amongst groups source of variation. Now this error then is the mean squares within, and then you have the total amount of error. So if you think about what we showed you in the beginning with the different sources of variation, we have the sums of squares total, the sums of squares within, or the sums of squares error, and the sums of squares among the groups. So in this instance, you have 84, 246. These are the numbers that we calculated. And again, I'm not going to ask you to calculate these on a test. And then if you add these two together, you come up with a total error of 331.23. 32, excuse me. And so this is the sums of squares t equals the sums of squares a plus the sums of squares e. Now the mean squares is the sums of squares divided by the degrees of freedom, which is 42.17 in this instant. The mean square error is the 246.99 divided by 70, so which is the 3.53. So the 242.17 and the mean square error is 3.53, so the F ratio is 11.95. So far what we've done is repeat what I showed you in the calculations. Now, how do you decide whether it was statistically significant or not? Well, you remember when I showed you the F table, and I showed you that you needed to have a numerator and a denominator? Well, in this instance, this is where it comes from, are these degrees of freedom. The numerator is the among groups degrees of freedom. So in this instance, it was 3 groups minus 1 is 2. And the denominator off of that table is the mean square error degrees of freedom. So this is the total number of people minus the number of groups, which is 70. And so what is the total degrees of freedom? Well, just like with the t-test, it's n minus 1. So what happens is that 2 of the degrees of freedom are used in the among group. The remainder are in the error group. So it's the 73 minus 1 is 72 minus the 2 degrees of freedom gives you the numerator number. So that's how these 3 degrees of freedom are calculated. So again, the F ratio is 11.95 with the degrees of freedom of 2, 70. So then what you would do is you would go to a table and you would find the degrees of freedom for a 2, 70. And in the book, they told us that the critical value was approximately 3.14. So let's go back to our table just in case to take a quick look at it. So while 70 in the denominator is not infinite, this is the best table we got for this example here. So what we're going to do is we're going to look at 2, since this is the number of groups in the numerator, and this will be infinite, so this would be our 70. So what we would do if this were a 70 here, we'd go 2 down to 70 for a 5% error. It's approximately 3. So as you can see from the textbook, it's not all that far off from what they told us in the textbook. So what we're going to do then is to compare this obtained critical value of 11.95 and compare it to the obtained F ratio versus the critical F ratio. The critical F ratio was 3.14, so the 11.95 is greater than the 3.14, so the omnibus test for the analysis of variance was statistically significant. That means that someplace amongst those three different comparisons, one of them was statistically significantly different. So let's take a quick peek at this convention again. The among errors variation is the sums of squares of the among group sums of squares divided by the number of groups minus 1. That gives you the mean squares. The total error then is the sums of squares error is equal to the sums of squares total, which is down here, minus the sums of squares among the groups, which was up here. And that is the number of people minus the number of groups. So in our example, it was 73 minus 3. And the sums of squares total and was the sum of then the sums of squares among the groups, the sums of squares error, and the degrees of freedom then that you should find total is the n in the total study minus 1. So the mean square among divided by the mean square error gives you then the F ratio. So this is the convention then for an ANOVA table that you should see in the literature. Final step in the hypothesis testing process is to draw and state the conclusion. So the actual conclusion is that the calculated F ratio is greater than the critical value of the F ratio of 3.14. So in this instance, the 11.95 is greater than 3.14. So that we are able to reject the null hypothesis of no difference and accept the alternative hypothesis of that one of the three conditions is significantly different from one another. So a difference does exist amongst the normal controls, the hypothyroid or the normal patients not on replacement therapy, and the patients on replacement therapy. So the inference is that the three populations were different after treatment. So the next question is, what two groups were statistically significantly different from one another? And that's where we come in with the idea of multiple comparisons. Now remember, one of our objectives was to describe and calculate how the degrees of freedom for each component of an ANOVA table are determined. And so we're going to take a second and to describe that a little bit more completely. Okay, so one of the objectives was something like, if given the following information, plus some additional background information, you should be able to determine what the appropriate statistical decision should be. So take a minute and think about this. If you were given the information F2, 24, which is the degrees of freedom, the 2 is what is in the numerator, and the 24 is what was in the denominator, is equal to 5.26, and the probability then was less than 0.05, what would your conclusion be with regard to the statistical decision? And secondly, what additional information would you need in order to make that appropriate statistical decision? So take a minute and think about this particular example and decide what you would do and why you would do it, and this will help you interpret the data from the literature. Okay, one of the other objectives that you've been asked to evaluate is to explain to a colleague why planned or a priori, that means in advance, analyses are sometimes necessary. And the answer is that sometime a clinical question or a theoretical question is known in advance, and so you only want to focus on those specific questions and not test all potential differences. And we'll get to post hoc comparisons, which basically means after this. And if you do post hoc comparisons in our example that we just gave, you would use three comparisons automatically. You would have to compare the situation where you have controls versus the normals, the controls versus the persons who are treated, and the normals versus the persons that are treated. But with an a priori explanation, you may not need three analyses, which would then make the adjustments that you have to make a little less onerous. And so by using two adjustments in advance versus three, your critical value then will be a little bit lower. So another objective is to explain to a colleague the meaning of an orthogonal planned comparison. Well, an orthogonal comparison is, as I said, a planned comparison or an a priori comparison, but it is a comparison in which you do not use the same information twice to evaluate two different comparisons. And I'll show you an example of what we mean by orthogonal comparisons. So let's take our three different groups, the mean of the control group, the mean of the normal group, those with a normal TSH who are not being treated, and the group that is being provided with the therapy, the hormone therapy. Now, in a non-orthogonal or a non-planned comparison, you would have to control this group versus this group versus this group, and the normal group versus the therapy group. So you would have three comparisons. Now, in this particular example, one of the things that I would like to know is there a difference between the groups of people that are not getting a medication, in other words, the control group and the normal group, compared to the one group who is getting the therapy. So what I would want to compare is groups 1 and 2 versus group number 3, because groups 1 and 2 are more similar because they are not getting the medication as group number 3 is. So we're looking at two groups with no medication versus the third group with a medication. So that's a theoretically or clinically relevant comparison. So we would do that one in advance. And what we do with the statistics software, and we'll show you it a little bit later on, is with these orthogonal comparisons, what we do is they look at a -1 and a -1, and this is what we put into the computer software for the orthogonal contrasts. And then we compare it to this group number 2 here, or think of this as a +2. So if we add this -1 and this -1, we come up with a -2 plus 2 is equal to 0. Now in the textbook they used 1/2 plus 1/2 plus 1. That's fine. You can use any combination of numbers that you want as long as the combination in these orthogonal contrasts come up to 0. Now, you could stop at this point in time, and then this would leave you your 0.05, and this is what sort of the Bonferroni test does. But on the other hand, you could also test 1 versus 2. Is there something about a person who is normal and a control versus someone who has a normal but who has a TSH that's in the normal range but has a hypothyroid condition? Is there something different or similar about those patients as well? So in this instance then they would be coded a -1 and a 1 to make those comparisons. So again, you can, in this instance we used these two right here. This is why it's not the same information. We used the information from these two together, so versus the therapy. So this is the combined information between the controls and the normals. The idea here is that they are more similar versus the therapy people. And in the second information, we now split out these two, and we compare number 1 versus number 2. And this makes it different information. It's not exactly the same because it is the average of these two pieces of information here. And here, this information is separate, and this information is not used at all. So all of the information that are used in those comparisons is separate information. And so in those orthogonal contrasts, then, you add up these coefficients. So minus 1 and 1 compared to 2, and then minus 1 and 1. See how this is assigned a value of 1, and here it was assigned a value of minus 1? Okay, so that's another indication that the information is different. So as long as those coefficients add up to 0, in this fashion, then the comparisons are orthogonal and they do not use new information. Okay? So this is with planned comparisons. Now, the other type of comparisons that we looked at with the t-test, for example, that is also appropriate with the analysis of variance, is what they call post hoc comparisons. And sometimes they are necessary because the omnibus test of the analysis of variance was statistically significant. In other words, the calculated F ratio was greater than the critical F ratio, but we don't know which pair of comparisons is statistically different. There is no a priori or in advance clinical indication as to why one set of comparisons should be significant and another should not be. So what they do is, in order to reduce the likelihood of experiment-wise error, we do post hoc comparisons and we adjust for this experiment-wise error. And we do that by dividing our original alpha error rate that we were willing to accept by the number of comparisons, and we adjust the alpha error downward. And that's what they call these post hoc comparisons. We try to reduce the amount of error. So in this instance, you take the 0.05 alpha error rate divided by 3, and the probability value then is equal to or less than 0.017. So we go to our tables of critical values in the t-test, and in the book it told us that the t critical value is approximately 2.47, and so rather than being the 1.96 as it would have been with the p of 0.05. So the critical value of t is somewhat higher, and since it is higher, it is more difficult to reject the null hypothesis than it would have been if we had capitalized on the experiment-wise error. There are a number of different types of post hoc comparison methods. I'll tell you this right now, that you are not going to have to know anything about these different types of comparisons other than the fact that the author should use one. If they have an omnibus ANOVA, which is statistically significant, and they have not identified the comparisons in advance, or they've not done a priori comparisons. If they just do an omnibus test and then they look at the value of the different mean scores and say this one is significant and this one is not, or they say that the p-value is less than 0.05, then you need to be concerned. Now, the one thing that if a person uses a Chaffee's test, this is the one that I generally will use because the Chaffee's test is the most conservative. And if the critical value exceeds the value in the Chaffee's test, then all of the others will then be significant as well. So the Chaffee's is the most conservative. Now, how does this work? Well, let's take a look at the example on page 175, which is table 7.75. In this instance, what they did was they compared the mean score of the control group T T4, the free T4, with the normal group, and they found that the difference between 13.55 and 14.00 was 0.45. Then they looked at the difference between the control and the group with the therapy and the free T4, and the difference between the 15.89 and the 13.55 then was 2.34. Then they compared the normal group with the therapy group, so the difference between the 15.89 and the 14.00 then again was 1.89. Now let's just take as one example here the honestly significant difference by Tukey and use this as our post hoc comparison statistic. In this case, we take the adjusted downward alpha level. So in this case, in order for our difference to be deemed statistically significant, the critical value needs to be greater than 2.49 times the mean square error divided by n. So in other words, what we're looking at is the standard error of the mean. So we multiply our 2.47 times the standard error of the mean, or in this case, the mean square error divided by the square root of n. And what we find is that the difference then has to be greater than 1.43 in order for that comparison to be statistically significantly different. So what we find then is the difference between the control and the normal group, again the 13.55 and the 14.0, is less than 1.43. So this is not statistically significantly different. And then what we find is that the patients who were provided with therapy were significantly different because each of these mean differences then is greater than 1.43. So the 1.89 is greater than 1.43 and the 2.34 is greater than 1.43. So under this circumstance then, the treatment, persons who were treated with replacement hormone therapy had higher values of free T4 than control patients and those who are considered to be the normal group. This can be done with all of the different types of post hoc comparison with the Chaffees, and in the book it showed that the Chaffees, the difference needed to be 1.48. And so you can see why that would have been a little bit more conservative, and that's because it was just a little bit higher. But even under this circumstance then, both of the groups that received therapy, or both of the therapy versus the other two group comparisons, would have been statistically significant in both cases. Okay, well, let's begin to look at a patient again. Okay, in this scenario, a study is being conducted that describes the impact of two drugs on the blood pressure of patients who are of different older age groups. The study is being designed to ascertain whether the factor with the most impact on the blood pressure is the medication or the patient's age. The patient's systolic and diastolic blood pressures were measured at the start and at the end of the study. So let's take a look at the aspects of the scenario that are most important. First of all, that it is being conducted on two drugs and different older age groups. Now, we have then one variable which is in the categorical level of measurement, and that is the type of drugs. And the older age groups infer that the patients have an ordinal, at a minimum, level of measurement. So the analysis of variance is appropriate because we have more than two variables, and within the older age group we have more than two groups. So analysis of variance would be important. Again, the blood pressure has a numeric or continuous level of measurement. So what we're trying to do is to figure out which of these two have the most impact on the patient. In this case, then, what we have is a 2, in this case exactly 2, but you can have a 2 or more way analysis of variance. So in our case, in this scenario, we have two different independent factors or variables, namely age and different types of drug therapy. So let's go back to our initial analysis of variance components chart. And what we described in our one-way analysis of variance is sums of squares, mean square within, between mean squares, or mean squares among the groups, the total error, the degrees of freedom, and the F ratio. Now, in a two-way or more analysis of variance, we also have two other types of pieces of information in the table called the main effects and the interactions. The main effects then are the two primary variables that we have in the study. So in this case, then it would be age by the drug therapy. Those would be the two main effects, age and drug therapy. And the interaction then is a statistical test that tests whether the effect of one of the variables has greater impact than the effect of the other on the dependent measure, or whether they have approximately the same effect within each level of the main effect. So the idea here is, that's a little bit confusing, so let me explain it a little differently. Does age affect all of the patients who receive drug A in exactly the same way as age affects all of the patients who were given drug B? So there may be, for example, some physiological factor that interacts with the pharmacology of the drug, so that patients who are older may respond to drug A differently than they do to drug B. So it may be then that the blood pressure effects of drug A is associated with age because persons who are older have poorer kidney function, poor lower serum albumin levels, and so forth. Okay? So we'll give a couple of examples of those interactions a little bit later on. So let's then get back to our chart where we decided upon whether to use analysis of variance or not. And the key thing here is all of these are similar, but the difference here now is the number of factors. Since we have two or more factors, then we use two-way analysis of variance or other ANOVA. And this means that we could have a three-way, four-way, and so forth. And we could also have an analysis of covariance. And we'll get to those a little bit later. Okay, well, let's take a look to see how two-way analysis of variance has advantages over the one-way analysis of variance. The easiest way is looking at it is that having two variables, you hope that you have twice as much ability to explain known variance or expected variance or desirable variance versus totally error variance, which is what you have with the mean squares within. So if we begin to look at our similar to what we had before, we now have the variance amongst the groups in factor 1. So let's say the groups are the drug variable in this particular instance. And you would hope that it explains some of the effects on blood pressure after a year's worth of treatment is the drug treatment group. But then you also have the factor group number 2, which is age. And as we know, age is associated with whether people have elevated blood pressure or not. And so what we're trying to see is if the age in this instance has an impact upon whether the patient blood pressure is controlled or not controlled, or how high the systolic blood pressure is. And so what ends up happening then is left over, you have less, or at least we hope, variance within the groups, which is also then known as the error variance. And so the more variance that you are able to explain as a result of your factors or your effects, the less variance that you have, which is error variance, if you think about it in terms of the total amount of variance being equal to the amount which is explained by the factors and the amount which is explained by the error, which is from within the groups. Okay, well that pretty much does it for today. What I'd like to do is to take a couple of minutes to go over the summary of what we talked about today and hit some of the highlights. The first thing that we did was we looked at a couple of more of the F distribution graphics, and for the first time showed how those graphs differed depending upon the degrees of freedom, much in the same way that the t-test changed with the degrees of freedom. And then we talked about the relationship between the t distribution and the F distribution. We also spent some time learning how to read an F distribution table, including the numerator, which was one part of the degrees of freedom, which describes the errors among the group or the variance among the groups, and the denominators, which describes the error within the groups. We talked about from the textbook calculation of the various sources of the components of a table of an analysis of variance. We talked about the calculation of the grand mean, the sums of squares, the mean squares, and the F ratio. And then after calculating those, we talked about what an ANOVA source table would look like and where each of those figures would be found within that source table. Next, one of the advantages of ANOVA is looking at multiple groups, but in looking at multiple groups, you sometimes don't know where the differences are, the mean differences, and the ANOVA table only tells you that there is a difference, not exactly where that difference is. In the last lecture, what I told you we would do is to look at various statistical tests that would be used after obtaining an omnibus test which was statistically significant. Well, that's what you do with planned and post hoc comparison. The planned comparisons are if you have a theoretical or clinical reason, you identify what those comparisons should be in advance. And the most frequent way of doing a planned comparison is to do an orthogonal comparison, where you do not use the same information in either one of the comparisons. Now the post hoc comparisons are done afterward, and this is basically a comparison amongst all of the groups in all of the tables. And this here is the most frequent way in which analyses of variance are done, is the comparisons are done afterwards. In this instance, then, you have a multitude of different ways of making those comparisons, and they each have their own advantages, but we're not going to ask you to compare and contrast the Chaffees with the Bonferronis with the honest significant difference and the least significant difference and so forth, only that you know that tests that do multiple comparisons across those groups need to use one of those tests. And then next we looked at the two-way analysis of variance, and one of the advantages of the two-way analysis of variance is for the first time amongst all of the statistical tests that we've done, we're able to look at two independent variables at one time, and how the two independent variables then help you to predict the outcome variable or the numeric variable. And then we talked about the different components of an analysis of variance test, and what we looked at with the two-way analysis of variance is, first of all, that there was an interaction possible, given the fact that now there were two independent variables. And those interactions are based upon looking at the two main effects. So in this instance, then, what we're looking at and calling a main effect are the two important independent predictors of the outcome. So in the case of some work that we have done, we've looked at gender and age, and those, or the drug, those would be a couple of independent factors or main effects. And then finally, we reviewed the components of variance in the context of a two-way analysis of variance, because the two-way analysis of variance is analogous then to the one-way. So that pretty much does it for the second lecture in this group of lectures about the analysis of variance. Hope it helped, and this is Dr. Doug, the Data Dude, signing off.